So this is about intermolecular forces. So I hope you got to watch the video last night, or the couple of videos, because I thought that was a good explanation. And I know some of you have completed this part of the Seneca learning, so hopefully this is not going to be too much of a step from what you've done so far. Now, you might have noticed there's different names for the different types of intermolecular forces. I think that is the key thing to watch out for. So in the video, I know that the presenter Mackham guy, I think he did mention van der Waals forces, but then he started talking about dispersion forces, induced dipole. So we are, right, just to be clear, van der Waals forces are the very basic force that we're going to meet. And then we call them permanent dipole-dipole attractions when they're between polar molecules. And then the last sort of special type of dipole-dipole attraction is a hydrogen bond. Okay, so what I'm going to do is just sort of start talking, assuming you've seen the video and so on. Let's just really start to look at the intermolecular forces, the types and so on. Okay, so intermolecular forces. So you've got three types that we're going to look at. Now remember that these only apply to covalent molecules. Okay, and I think we mentioned in the last video, if there's a molecular ion that has covalent molecules between the atoms, but has an overall positive or negative charge, this is not going to apply, right? If it's something like NH4 plus, if it's H3O plus, if it's NO2 minus or NO3 minus or whatever it is, right? Sulfate. Okay, all of those are going to form ionic bonds, right? Because they have a full negative or positive charge, right? They have lost or gained electrons. So they are ions, they form ionic bonds. So they will not partake in this kind of intermolecular forces here, right? They have other things going on. So we're going to look, so let's take those away. Okay, so covalent molecules only, polar, non-polar, well, yes, all types. Okay, and atoms, in fairness, individual atoms as well, like in the noble gases. So the first type of intermolecular force is the van der Waals force. Say in the English boards, they call it London forces, London dispersion forces, induced dipole interactions. They all, well, and I have to admit that the English are, in this instance, correct. Van der Waals forces actually is not the best term, but it's the one that CCA uses, so we'll use it. Okay, so there's van der Waals, and then you have permanent dipole-dipole attractions. And then lastly, you have hydrogen bonding, the strongest type of intermolecular force. Now, as I say, there was something raised, just a video I saw recently, it was saying that, you know, the difference between bonding and forces, intermolecular forces, they're all connections that require energy to break. You know, these ones are in between molecules and they're weaker than, say, the covalent bonds and all, but really all of these are bonding, right? Bonding is the description of what, you know, what holds particles together. Okay, so just be aware of that. We're classifying these as intermolecular forces, but effectively they are a type of bond. And I suppose hydrogen bonds become called that rather than attractions because they are seen as quite strong. But I mean, there's a spectrum of strength, if you like, of different types of bonds. Okay, but the key thing about these is they are in between molecules, right? Now, the causes, right? What gives rise to each of these intermolecular forces? Right, so van der Waals forces are called by induced dipoles, right? And it's influenced by the number of electrons. So every electron will give an induced dipole. So more electrons, more van der Waals forces, right? So that's caused by the number of electrons. Now we'll see that, and when you're reading the notes after, you'll see that the larger the molecule, or the more electrons a particular particle has, the more van der Waals forces it has, and the more energy it will take to break them. And just bear in mind here that intermolecular forces influence particular properties, which are particularly melting point and boiling point. Okay, they're the real ones, and solubility as well. It's something we'll meet this year. Okay, but mainly melting and boiling point. We're really going to be talking about that. So the stronger the forces of attraction, the higher the melting and boiling point of a particular substance is going to be. And you can measure that, obviously, and that then tells you something, it gives you information on how strong the forces are within, you know, at the atomic and molecular level. Okay, so they're caused by that, right? Permanent dipole-dipole attractions are caused by attraction between dipoles, between polar molecules, delta plus and delta minus, parts on adjacent molecules. Okay, so they have to be between molecules, right? And hydrogen bonding is also caused by the same thing on hydrogen, right? Really the delta plus of hydrogen and the delta minus on nitrogen, oxygen, or fluorine in an adjacent molecule. Pretty much. We'll have to modify that actually, right? So I should actually modify that. It's the delta plus on a HF, a HO, and a HN bond, and the delta minus on a nitrogen, oxygen, fluorine in an adjacent molecule. So it can be a CN or a CO or whatever it is, CF, right? Okay, but we won't have to worry about that just yet. Now, the caused by those, right? Now let's have a look at examples of where you will get each of these intermolecular forces set up. Right now, can I just say that all, right, where only van der Waals, substances with only van der Waals are non-polar. Right, but I should say that because all molecules have electrons, right, they all actually have van der Waals forces. But if you have only van der Waals forces, it's non-polar molecules. So anything with like CH4, F2, anything at all that has non-polar bonds, BR2, S8, C2H6, right, ethane, anything at all like that. Okay, they have only van der Waals. What sort of molecules have, or what sort of substances have permanent, well, they're going to be compounds, have permanent dipole-dipole attractions, so those with polar bonds. So for example, CHCl3, HCl, what else could you have? Carbon monoxide, not carbon dioxide, I should put that over here because it's non-polar overall. And no, not NH3, it's going to go over there. The H3Cl, CH2F2, I'm trying to think of the common ones, SO2, SH2, because they have lone pairs, they're going to be polar molecules, polar bonds. That's actually HS2, H2S. Okay, there's some examples of those, right? So polar molecules will have, they will have permanent dipole attractions, so and van der Waals, right? So they'll all have van der Waals, okay, because they all have electrons, but they'll be weak. They'll be, the permanent dipole attractions are going to be the most important intermolecular force in these type of molecules. And then lastly, hydrogen bonding. Now, these are very limited, so, and these are caused because of the huge electronegativity difference between the hydrogen and fluorine, hydrogen and oxygen, and hydrogen and nitrogen. So we'll only worry about pure compounds now, that the sort of the rest of it is going to be more relevant when we look at organic chemistry. So there's only a range of substances where this will apply. HF, that's the only compound that has hydrogen, a HF bond. You can't get, they each can only bond to another. NH3, right, and H2O. Okay, so those substances, those pure substances will have hydrogen bonding within them. Now, they will form hydrogen bonds with other substances as well, but I think we're going to leave that for now and just be aware that hydrogen bonding is much more limited than the permanent dipole-dipole attractions. But because it's because it helps explain solubility, and it's very important in organic chemistry as well. It actually will be quite a large topic that we'll meet again in AS2. Okay, given that, I foolishly left questions out of this section. So what I want you to do is, I'm going to send you a sheet that has, it's trying, right, I want you to read, at this point I want you to study the information in your notes, which is frankly far too much. And I would like you to pull information, I would like you to try and summarize what's there using whatever method you can. Okay, so I really have, I think I copied it from Chem Guide, and I just have far too much detail in it. But I want you to really be able to explain the difference, you know, the main effects on boiling points and how to compare different substances to each other. Okay, so I do have summary points in the booklet, and that's probably the first place to go. And I have a summary table at the back, which doesn't look very summary-like. So I think if I were you, I would take that and chop it right down. And then there are questions on page 35, just about polarity. Oh yes, actually page 35 looks pretty useful. So I'd like you to do the questions on page 35 after you've had a read of the notes as well. Okay, so I'm going to send you another document as well. So please check Google Classroom. So you're going to do page 35, and then you're also going to do the document I sent you on Google Classroom. Okay, thank you.